Okay, in this video, we're going to be looking at the 1999 AB calculus exam. So, this question, we have a particle that's moving along the y-axis, so it's moving up and down, with this velocity for a positive t value. And then in part A, we're asked, in which direction is the particle moving at time t equals 1.5? So you should know that if the velocity of the particle is positive, so if velocity is positive, then it's moving up. It's going up. If velocity is negative, then it's going down. So at time t equals 1.5, is the velocity positive or negative? And the way we figure that out, you just take 1.5 and we plug it into this velocity function. So it'll be v of 1.5 is 1.5 times sine of 1.5 squared, and that comes out to be 1.167. And then since v of 1.5 is greater than 0, the particle is moving up. It's going up. And in terms of points, you get 1 point for writing a statement that says that the particle is moving up. I wouldn't draw the arrow though. Okay, so part B, find the acceleration of the particle at time t equals 1.5. Is the velocity increasing? So first, let's find the acceleration. And you find acceleration by taking the derivative of velocity. So we'll be taking the derivative of velocity, where a of t is v prime of t. So it's going to be the derivative of t sine t squared. And if we do that using the product rule, we're going to get t times cosine of t squared times 2t plus just sine of t squared. I can simplify that a bit and get 2t squared cosine t squared plus sine of t squared. Okay, and then now this is my function for the acceleration, but the question is asking for the acceleration at time t equals 1.5. So we'll just plug in 1.5 into this equation there, and it's going to give me 2 times 1.5 squared times cosine of 1.5 squared plus sine of 1.5 squared, and that comes out to be negative 2.049. And okay, well that's the first part of our question there. And the second part of the question is asking, is the velocity of the particle increasing? So if the velocity is increasing, then the acceleration is going to be positive, and if the velocity is decreasing, then the acceleration is going to be negative. And since in this case we have a negative acceleration, our velocity is going to be decreasing. So the question is asking, is the velocity increasing? Well, no, it's decreasing because the acceleration is negative. So that would be our justification. I'm not going to write it out, but you'd say something along the lines of, since v prime of 1.5 is less than 0, velocity at time t equals 1.5 is not increasing. And it's important to not use a of t and instead use v prime of t, because you should try to not use functions that they don't specifically give you, like they gave us v of t here. So don't use a of t, just use v prime of t in your explanations. Okay, and for points, you get 1 point for the answer and 1 point for the explanation. Okay, so part C, given that y of t is the position of the particle at time t, and that y of 0 equals 3, find y of 2. Okay, so now you should know that, like the same way that acceleration is the derivative of velocity, we can go the other way. And say that position is the integral of velocity. So to find the function of the position as a function of time, we're going to integrate the velocity function with respect to time. So that's the integral of t sine t squared dt, and then we're going to use a u substitution here because there's the term and its derivative. So u is t squared, du is 2t dt. Therefore we can rewrite this integral as 1/2 the integral of u, or not that, it's going to be sine of u du, which is negative 1/2 cosine of u plus c, which is negative 1/2 cosine of t squared plus c, because you use t squared. And then now this is the function for the position as a function of time, but to find the constant value c here, we have to use the initial condition that y of 0 is 3. We can say that since y of t is negative 1/2 cosine t squared plus c, I can plug in my point 0, 3 in here, which is going to give me 3 is negative 1/2 cosine 0 plus c. Therefore, c is 3 plus 1/2, which is 7/2. 7/2. Okay, so that's not really our answer, but that's part of the problem. So now the full position function is negative 1/2 cosine t squared plus 7/2. I'm gonna erase that because it's kind of confusing. That's not our final answer. Okay, that's good enough. So, anyways, now that we have our position function, we can look at what the question is actually asking. Find y of 2. Well, now that we have a function for y of t, it's just as simple as plugging in 2 in for t. So, y of 2 is negative 1/2 cosine of 2 squared is 4 plus 7/2, and this comes out to be approximately 3.827, if you can read that. Okay, and points, you'd get 1 point for understanding that position is the integral of velocity and setting up this integral. You'd get another point for correctly solving it as negative 1/2 cosine t squared plus c, and you'd get a third point for the correct answer. Okay, so part D. Find the total distance the particle travels in from time t equals 0 to time t equals 2. Okay, so now the word distance, that signifies that we're talking about speed, not velocity. So the key thing to understand here is that speed is the absolute value of velocity. So velocity can be negative, but speed can never be negative. So I can write the function of speed as the absolute value of the velocity function. So the speed is the absolute value of t sine t squared. Okay? And then now we want to find the total distance traveled from t equals 0 to t equals 2, and we're going to have to integrate this function, the speed function, from 0 to 2, similar to how we integrated velocity earlier on. We're going to integrate speed, so we're going to integrate this absolute value. There. And if you evaluated that in your graphing calculator, you would get 1.173. And despite how short this problem was, it carries a lot of points. You're going to get 1 point for setting up the bounds correctly. You're going to get 1 point for dealing with the fact that this is speed. This is the fastest way to do it, by setting an absolute value. But you could also find all the points the velocity changes signs. I think that's just a lot harder, but you get 1 point for figuring out a way to deal with the negativeness of the velocity. And then you get a third point for your answer. So it's a really, really short question. It took like, what, 20 seconds? That's 3 points. And now we're done with question 1, and let's look at question 2. Okay, so question 2, we have this shaded region R, which is this like gray part, bounded by y equals x squared and y equals 4. So in part A, we're asked to find the area of R. Okay, so this is going to be a pretty simple question. So first we've got to find the intersection points, the x coordinates of those two values. So we're going to do it by setting x squared equal to 4 and finding that x is equal to plus or minus 2. So the bounds are going to be negative 2 and 2. And then finding area, we're going to have to integrate from the bounds, on the bounds negative 2 to 2, of the top curve minus the bottom curve. So let's set that up. It's going to be the integral from negative 2 to 2 of the top curve is y equals 4 minus the bottom curve is y equals x squared, and this is dx. And a little trick you can do, since the function is like the same on both sides here, we can rewrite this as 2 times the integral from 0 to 2 of 4 minus x squared dx. And that just makes the calculations easier because 0 is one of the bounds. And then when we evaluate this, we can write this as 2 times 4x minus x cubed over 3, being evaluated from 0 to 2. And then if you plug in your numbers, you're going to get 2 times 4 times 2 is 8, minus 2 to the third power over 3. And we don't need to simplify that, that's good enough. That's our answer for part A. And this is a 2-point question, one for writing the integral and one for solving it. Okay, so now let's look at part B. Okay, so part B, find the volume of the solid generated by revolving r around the x-axis, or around this line here. First, let's identify our two radii, and we're going to have two radii because we have like these two separate curves that are both a different distance from the axis. So we have one radius right here, small radius, which goes from the x-axis to the parabola. And then we have the second line, the second radius, which goes from the x-axis to the line y equals 4. And let's identify the lengths of the two radii. So the big one is going to be from 0 to 4. So the big radius is going to be a constant value of 4. And then the little radius is going to be this distance. So it's going to be from 0 to x squared. So this distance is going to be x squared. And then now you should know that, well, now that we identify the two radii, the formula is simply pi, the integral from a to b, of big R squared minus little r squared. So now it's just a matter of plugging in our numbers. And remember, the bounds is the same thing as before. It's -2 to 2. So specifically for our case, it's going to be pi times the integral from -2 to 2. Big R is 4, so 4 squared, minus little r, minus x squared squared dx. And then we can use the same trick we did before by replacing one of the bounds with 0 and then putting a 2 in the front, because this is a symmetrical graph. From 0 to 2, well, 4 squared is 16, minus x squared is x to the 4th dx. And then actually doing the integral now, we have 16x minus x to the 5th over 5. And then again, the bounds are 0 and 2. So now just plugging in, we're going to get 2 pi times 32 minus 2 to the 5th over 5. And now looks like a good place to stop with this problem. In terms of points, we're going to have 1 point for, first of all, having the constant pi or 2 pi out here, and then for also including the correct bounds. You get another point for correctly putting the right stuff in the integral, the integrand. And then you get a third point for having a correct answer. Okay, let's look at part C now. So in part C, we have some number k where k is greater than 4, such that when r is revolved around the line y equals k, the resulting solid has the same volume as the solid in part B. Right, but do not solve an equation involving an integral expression that can be used to find the value of k. Alright, so what this problem means, first we should try to figure that out. There exists a number k is greater than 4, such that when r is revolved around the line y equals k. So there's going to be a number that's greater than 4, so it's up here somewhere, where y is equal to k. So we're going to have some horizontal line here at y equals k, such that when we revolve this solid, the same solid r, around this, and we're going to have this little gap here, the resulting solid will have the same volume as the volume we got in part B. So what my thought process is first we should set up an integral expression to find the volume in terms of k, and then we should set that equal to the answer we got in part B, since we want them to be the same. So first let's find an integral expression for the volume in terms of k. Again, let's identify our two radii. Our first radii is going to be going from the line y equals k to this distance here. This is the small radii, it looks like. And then the big radii is going from y equals k to the other curve. So I'll call little r, which is this small one here, that's going to be this whole distance k minus this distance 4. So k minus 4. And then our big R is going to be this whole distance k minus this distance x squared. So it's going to be k minus x squared. And then setting up our expression, I'm just going to skip just writing 2 pi and then 0 and 2. It's really the same thing over and over again. And then so remember the formula is big R squared minus little r squared. So plugging that in, we're going to have k minus x squared, this is our big R, and then k minus 4 squared, this is our little r, dx. And then we want this to be equal to the volume we got in part B, right? And the volume we got in part B, if you remember, was 2 pi times 32 minus 2 to the 5th over 5. So this is an integral expression that can be solved for k. It's probably a lot of work, but you can do it, and you'll get the value of k, such that if you revolve it, you'll get the same volume as we got in part B, right? Because we set those equal to each other. And in terms of points, you get 1 point for the limits and the constant term. You get another point for this k stuff in here, and you get another point for setting it equal to what you got in part B. Okay, now let's move on to question number 3. Okay, so question 3, we have water flowing out of a pipe given by a differentiable function r of time t. The table above shows the rate as measured every 3 hours for a 24-hour period. This table here. And for part A, we have to approximate the integral from 0 to 24 of r of t by using a Riemann sum with 4 subdivisions of equal length. That's nice. Equal length is pretty rare on the AP exam, so it's a little nice touch they give us. Using correct units, explain the meaning of your answer in terms of water flow. Okay, so Riemann sums. To find the midpoint Riemann sum with 4 divisions of equal length, we're going to use this formula. It's going to be the common base times r of t0 plus t1 over 2. This is where the midpoint part comes in. Plus r of t1 plus t2 over 2 plus ... And, well, what's the base and what's the t values that we're going to use? Well, let's look at the question here. They want 4 subdivisions of equal length, right? So since we're approximating from 0 to 24 with 4 subdivisions of equal length, each subdivision is going to be 24 over 4, or 6 long. Okay, so the common base is going to be 6. We're going to have 4 different groups of 6. So that means we're going to have 6 times r of, and then what are the t values? Well, we're going from 0 to 6, 6 to 12, 12 to 18, and 18 to 24. So those are going to be the t values, 0, 6, 12, 18, and 24, that I'm going to use in the equation. So I'll have 0 plus 6 over 2 plus r of 6 plus 12 over 2 plus, you can see where this is going, 12 plus 18 over 2 plus 18 plus 24 over 2 plus, oh no, that's it, yeah, that's it. Because we did 1, 2, 3, 4 equal subintervals, each of them being 6 in length, and we're going to use this to approximate the integral from 0 to 24. Let's simplify this a bit by, solving these numbers here. 0 plus 6 over 2 is 3. 6 plus 12 over 2 is 9. 15. And 21. And then how are we going to get r of 3, r of 9, and so on? Well, we're going to use this table that they gave us. So r of 3 is going to be, at time t equals 3, the r value is 10.4. So r of 3 is 10.4. And then r of 9, we're going to look at 9. And then r of 9 is 11.2. So like that for the other two values as well, we can fill this in. This is 10.4. This is 11.2. This is 11.3. This is 10.2. And if you did that out, you would get 258.6. And let's look at the units now. If we're finding the approximation of an integral, the integral is the area under the curve, and the units for the area under a graph is the units for the two axes multiplied together. So gallons per hour times hours, and then gallons per hour times hours is just going to give us gallons. So the units for the answer is going to be gallons. And then that was one part of our answer. The second part is using correct units, explain the meaning of your answer in terms of water flow. So again, this is the area under the curve. This is like the total water flow, because the rate at which the water is flowing out of a pipe as a function of time. So if we take the integral of that, we're going to take all the water that's flowing in the pipe throughout the entire time interval. So if we wanted to write that out, we'd say, well, the integral is the approximation of the total water flow in gallons from the pipe in the first 24 hours. And we did use correct units because the units would be gallons, right? So that was that. And then in terms of points, we'd get 1 point for setting up the Riemann sum, like so, and then we'd get another point for the answer at the bottom. That was part A. Let's look at part B now. Okay, so part B, is there some time t where 0 is less than t is less than 24 such that r prime of t is 0? Justify your answer. Again, so there's no like nice function r that we can differentiate and set equal to 0 to easily figure this out. So we're going to have to use a little bit of interesting logic. Well, not that interesting, just going to be logic. Looking at this table here, so we're looking at time t equals 0 to t equals 24, so let's look at those two values specifically. T equals 0 and t equals 24. And something that we notice right away is that the r of t values are the same. So if we were to find the average rate of change, which remember is f of b over f of b minus f of a over b minus a, that's going to be r of 24 minus r of 0 over 24 minus 0, which is 9.6 minus 9.6 over 24, which is 0. Well, the average rate of change is 0. Therefore, you should remember the mean value theorem, or if you want to get specific, in this case we can use Rolle's theorem. We can use that. You can use those theorems to say, well, since r of 0 equals r of 24, the average rate of change is 0. Therefore, by Rolle's theorem, or by the mean value theorem, there exists a value t where 0 is less than t is less than 24, such that r prime of t is equal to 0. Because remember, what that means is, since it's going up and it's going down, the function looks probably something like this, right? And then, well, since this average rate of change here is 0, there's some point on the graph where its derivative is also 0, like that. So we justified our answer and we said yes, there is some time t where 0 is less than t is less than 24, such that r prime of t is equal to 0. That was just a 1 point question. You'd get 1 point for correctly saying the right response and for justifying it. Okay, so let's look at part C. The rate of water flow, r of t, can be approximated by q of t. Okay, so now we have like a concrete function to deal with. That's really nice. The rate of flow q of t, and now use q of t to approximate the average rate of water flow during the 24-hour time period. So in part B, we looked at the average rate of change, and now we're going to look at the average value of a function. Here's where we're going to use integrals. The average value of a function is, well, just for a general function, it's 1 over b minus a times the integral from a to b of f of x dx. And then in our specific case, we'll say, well, we want to approximate the water flow during the 24-hour period. So we're starting at t equals 0, and we're going to t equals 24. So it's 1 over 24 minus 0 is 24, times the integral from a to b, the integral from 0 to 24 of f of x. We're going to be using q of t, so 179,768 plus 23t minus t squared, that dt. And then this is the average rate of water flow. This is just going to be plugging into the calculator, and you're going to get 10.785. And then again, looking at units, we want to find the average rate of water flow. Well, that's just going to be some rate of water flow. So the units for the rate of water flow is going to be the same for the units of the average rate of water flow. And so therefore, this average is going to be the same units that we use for r of t and q of t. And since r of t is measured in gallons per hour, as you can see up here, this average water flow is also going to be measured in gallons per hour. Okay, and then for points, you'd get 1 point for the limits and the 1 over b minus a. You'd get another point for a correct integrand, and then a third point for the right answer. And then overall for this whole question 3, you'd get 1 point for including the correct units. In part A, we had to write gallons, and in part C, we had to write gallons per hour. Okay, so that's question 3. Now let's look at question 4. Okay, question 4. Suppose that the function f has a continuous second derivative for all x, and we're given a bunch of values for x there. Let g be a function whose derivative is given by yada yada yada, and notice that f of x is in the derivative of g of x. So g of x and f of x are going to be very closely related functions. And then part A, write an equation of the line tangent to the graph of f at the point where x equals 0. Okay, so if we want to write an equation of a line, some information that we're going to need is we're going to need mainly two pieces of information. First, we're going to need the slope of the line, and then second, we're going to need at least one point on the line. So we want to find the line tangent to the graph of f at the point where x equals 0. So we need, for this line, we need to find a point and the slope. Well, we know that f of 0 equals 2, so the point 0, 2 lies on the graph of f. So that's a point. And then we also want to find the slope. Well, the slope of a function is going to be its derivative at a certain point. So if we want to find the line tangent to the graph of f at the point where x equals 0, we need to evaluate the derivative at x equals 0, and that'll get us the slope of the tangent line. Okay, and then looking at this here, we know that the slope, which is the derivative of f of x at x equals 0, is -3. So the slope of f of x at x equals 0 is -3. And we have our slope, we have our point. Now we can use our point slope form. Y minus y1 equals m times x minus x1. Right? And then we don't really have to solve this. You can if you want and put it into like y equals mx plus b, but honestly this is good enough. Just a quick 1 point question. You get the 1 point for getting that equation correct. Okay, so part B, is there sufficient information to determine whether or not the graph of f has a point of inflection when x equals 0? Explain your answer. Okay, so if we have an inflection point, what does that really mean? Well, it means that at an inflection point, the concavity of f of x switches. So it goes from concave up to concave down, or concave down to concave up. And the way we determine a concavity is by looking at the second derivative. So if f of x has a point of inflection when x equals 0, its second derivative is going to switch signs. So the second derivative, f double prime of x, is going to switch signs. And it's clear that if the second derivative switches signs, it's going to go from negative to positive, so it's going to cross through 0. And if it goes from positive to negative, it's still going to cross through 0. So we can say that f double prime of 0 has to equal 0, because we're looking at the point where x equals 0. Well, we know this first condition is correct. F double prime of 0 is 0, so we're half the way there. And now we need to see, does f double prime of x switch signs? Well, there doesn't really seem to be a way to determine that given our information. We really don't know f double prime values for anything other than x equals 0. So for all we know, the graph of f double prime of x could look something like this. If this is the xy coordinate plane, the graph could look something like this. Second derivative, it's coming up to 0, and it just touches it, and then it goes back down or something. So it could look something like this, where the second derivative of f is 0 at x equals 0, but it doesn't switch signs. As far as we know, this is what it is. We don't know whether it switches signs or not, so there is not sufficient information to determine whether or not the graph of f has a point of inflection where x equals 0, because we don't know if it switches signs. If we wanted to know this, they would have had to given us like f double prime of -1 and f double prime of 1, for example. Okay, but as far as we know for now, there is not sufficient information, and that was part B. You'd get 1 point for the correct answer there, and then 1 point for a correct explanation. Okay, part C. Given that g of 0 is 4, write an equation of the line tangent to the graph of g at the point where x equals 0. Again, we want to find the equation of a tangent line, so we're going to need the point and the slope, the two keys to the point slope form. Well, the point is pretty easy. We know that g of 0 is 4, so the point is 0, 4. The slope is going to be a bit trickier. So, let me just do that real quick. Okay, so to find the slope, we're going to have to take the derivative of g of x to find the instantaneous slope where x equals 0. So to take the derivative, we'll take g prime of x, And it's pretty nice that we have an equation for g prime of x right here that we can use to find the slope. Okay, so if I wanted to take g prime of 0, which is what we want because we're at x equals 0, I just plug in 0 into the function and see what happens. So e to the negative 2 times 0 is going to be 1, because e to the 0 is 1. And then 3 times f of 0 plus 2 f prime of 0. F prime of 0. Right, like I said, this is just going to 1. And then 3 times f of 0. How do we figure out 3 times f of 0? Well, the way we figure out f of 0 and f prime of 0 is by looking at the information they gave us of f and its derivatives evaluated at x equals 0. So we know that f of 0 from this table, or from this list rather, f of 0 is 2. So we have 3 times 2 plus 2 times, what's f prime of 0? Well, f prime of 0 is negative 3. So we have a negative 3. And then this comes out to 6 minus 6, which is 0. So our slope is 0. Erase this g prime of x here and replace it with 0. Okay, so now we have the point, we have the slope. Let's put it into point slope form. Y minus 4, 0, x minus 0. And I'll just simplify this because why not? Get y equals 4. In terms of points, you get 1 point for taking the derivative of g and another point for the correct answer. Okay, part D now. Show that g double prime of x is blah 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 blah, and does g have a local maximum at x equals 0, and justify your answer. Alright, so g double prime of x. The first thought that comes to mind is just taking the derivative of g prime of x, and since this answer also contains f primes, f of x, f double prime, that's probably the right way to do this. So there's no shortcut. We just have to, tough it out and do the product rule and see what happens. So we're gonna have e to the negative 2x times the derivative of this, which is 3 f prime of x plus 2 f double prime of x plus negative 2 e to the 2x, or e to the negative 2x, times stuff here, 3 f of x plus 2 f prime of x. And now it's just a matter of simplifying this long guy here. I can have an e to the negative 2x here, and e to the negative 2x here. So I'm just going to pull that out completely. I'll get e to the negative 2x, and then left over I'll have 3 f prime of x plus 2 f double prime of x plus negative 2 times 3 f of x plus 2 f prime of x. Can I squeeze it in there? Yes, I can. Okay. Now let's simplify this middle part here. E to the negative 2x. So we're gonna have we'll start with this guy here. We're gonna have negative 2 times 3 is negative 6 f of x. So I'll bring that to the front. And then for the f primes, I'll have the negative 2 going there. I'll get a negative 4. And I have the 3f prime of x minus 4f prime of x. That's going to be minus f prime of x. And then I just have the plus 2 f double prime of x here. And then let's go look at that. We have e to the negative 2x times this and that and that. It looks to match up. So we did the g double prime of x correctly, and there's our answer. Okay. And then the second part of the question, does g have a local maximum at x equals 0? So what does it mean to have a local maximum? Well, it means that your first derivative is 0. So to have a local maximum, your first derivative is 0. So g prime of x at x equals 0, s equals 0. And then the second derivative, g double prime of x at x equals 0. Well, since it's local maximum, the derivative has to be going to 0, and then it has to be going on. So the second derivative has to be less than 0. So are these two things true? Well, remember in part C, we found the slope at x equals 0, and we found that it is 0. So this is true. And then the second part is g double prime of x at x equals 0 less than 0? Well, that would be through plugging in 0 into this expression here. So g double prime of 0 is going to be e to the 0, which is 1, times negative 6 f of 0 minus f prime of 0 plus 2 f double prime of 0. Okay, and then f of 0, f prime of 0, f double prime of 0. We know all three of these values from up here. They're 2, negative 3, and 0. So that's going to be negative 6 times 2 minus negative 3 is plus 3. So that's negative 12 plus 3 is negative 9. And negative 9 is negative. It is less than 0. So this second condition, g double prime of x at x equals 0 is less than 0. This second condition is met as well. Therefore, our g of 0 is a local maximum. And the way we prove that, because it says justify your answer, you're going to have to say, well, we looked at g prime of x at x equals 0, and that's 0. We looked at g double prime of x at x equals 0, and that's negative. And looking at those two conditions, we can reasonably conclude that g of x has a local maximum at x equals 0. And in terms of points, you get 2 points for performing the second derivative correctly. You'd get 1 point for finding out g prime of 0 is less than 0, and you get 1 point for correctly justifying using your g prime of x and your g double prime of x reasoning. Okay, so I think, yeah, now we're finished with question 4. Let's move on to question number 5. Okay, let's look at question 5. We have a graph of the function f with 3 line segments, 1, 2, 3, and we have the function g of x, which is the integral from 1 to x of f of t dt. And when you see this kind of integral with x in one of the limits, the first thing you should think about is the fundamental theorem of calculus, where if we take the derivative of this, we're just going to get f of x. So that's probably going to come to this problem at some point. But anyways, let's look at part A. Compute g of 4 and g of negative 2. So first we'll look at g of 4, and that's just going to be plugging in 4 for x. So that's the integral from 1 to 4 of f of t dt. So that's the area from 1 to 4, so this whole area, right? And we notice that the area from 2 to 3, like this section and then this section, they're like the same in magnitude, but this one is positive and this one is negative. So these are going to cancel each other out. So now we're just left with this area. So we have this 1 by 1 square, so it's going to have 1 by 1 plus this triangle, which is 1/2 times 1 times 3, and that comes out to be 5/2. Okay, and then we also need to compute g of negative 2, which is the integral from 1 to negative 2 of f of t dt. And this is kind of weird how like the top number is less than the bottom number, and the way we fix that is we just put a negative sign in the front and then switch the bounds. So now we'll be going from negative 2 to 1 of f of t dt. Right, we switch the bounds and put a negative sign. And then now, so that's from negative 2 to 1, that's just this triangle. Let me erase this, and then we have this triangle there. So the area of that's going to be 1/2 times 3 times 4, and there's also the negative sign, don't forget that. That's going to come out to negative 6. And this is a 2-point question, one for each of the 2 things. Okay, and then part B, find the instantaneous rate of change g with respect to x at x equals negative 1. Okay, so when you see like this kind of words like rate of change or anything like that, you should think of derivatives. So the instantaneous rate of change of g is going to be g prime of x. right? And then, so the g prime of x, since g of x is this integral, the derivative of g is going to be the derivative of this integral. So g prime of x is equal to the derivative of the integral from 1 to x of f of t dt. And remember how I said, like, this is probably going to come into some point. If we take the derivative of this kind of an accumulation function, you're just going to get f of x. Okay, so now we know that g prime of x is equal to f of x. Let me just rewrite that. G prime of x is equal to f of x. And then anyways, so we want to find the instantaneous rate of change at x equals 1. So the question is, what is g prime of x when x equals 1? So what is g prime of 1? Well, that's going to be equal to f of 1, right? Since g prime of x equals f of x. So now the question is, what is f of 1? Well, we can look in this graph of f of x. At x equals 1, f of x is 4. So this is equal to 4. And therefore, the instantaneous rate of change of g is also 4. And this is just a quick 1-point question for getting the right answer. And then part C, find the absolute minimum value of g on the closed interval -2 to 4. And this is a really good question because we really have to understand what's going on with this graph here. So if we want to find the absolute minimum value, that's going to be, since g is the area under this graph f, if we want g to be at its absolute minimum, we want the area to be at its absolute minimum, right? So to figure out where the area under the curve could be the lowest, let's just take a look at the graph. Since the graph is increasing all along here, it's going to be accumulating more and more area until it gets to 3. So from anywhere from -2 to 3, since the area keeps increasing, the lowest it could ever be is at x equals -2. So we have a candidate minimum at x equals -2, right? And then from 3 to 4, the area is decreasing, so the area gets lower and lower. So that means if we want to find the lowest area, it's going to be all the way here at x equals 4. So we also have another candidate minimum at x equals 4 as well. So the question is now, which of these two is the actual absolute minimum, right? So since we want to figure out which of these is the minimum, we can plug both of these x values into g and find out which one gives the lowest value for g. We know the absolute minimum is going to be one of these two. Just the question is, which one is it? So g of -2 and g of 4, right? Well, actually, if you look at part A, these were the two things we were asked to calculate. And g of -2 came out to be -6, and then g of 4 came out to be 5/2. So we know that the area is lowest at either this point or this point, and since -6 is obviously less than 5/2, this is the absolute minimum. And to be really specific, it says find the absolute minimum value, right? That's asking for the y value. If it asked for the x value, it would say what is the x value of the absolute minimum. But the keyword value here tells us they want the y value, so the absolute minimum is -6. And then since it wants to justify our answer, we'll say that since f of x is positive on -2 to 3, the minimum area is at x equals -2, and since f of x is negative on 3 to 4, the lowest area is at x equals 4, and testing both of those points gives that g of -2 or -6 is the absolute minimum for g. And in terms of points, you'd have 1 point for like looking at the fact that the function is positive here and negative here. You'd get another point for identifying these two as your candidate points. And you get a third point for correctly figuring out that -6 is the absolute minimum and not 4, or g of 4. Okay, now let's look at part D. The second derivative of g is not defined at x equals 1 and x equals 2. How many of these are x-coordinates of points of inflection on the graph of g? And justify your answer. Okay, so when you see points of inflection, that should trigger in your mind the second derivative. Because when you're checking for points of inflection, you have to take the second derivative of the function you're taking the points of inflection of. So since we want to find the points of inflection on g, we're going to take g double prime of x. And since g prime of x is f of x, g double prime of x is f prime of x. Right, since g prime of x equals f of x. Just a little thing. And then, so let's think about what an inflection point is now. An inflection point is when the second derivative switches sign or direction, right? So we're asking how many of these x equals 1, x equals 2 are both of these inflection points. So does the second derivative switch at x equals 1 and at x equals 2? Right, so we're asking is does g double prime of x switch sign at x equals 1 and x equals, that's not an and, that's an at. X equals 1, x equals 2. And well, what happens when g double prime of x switches sign? Since g double prime of x is equal to f prime of x, we can replace the g double prime of x here with f prime of x. F prime of x. So now we've rewritten the question as, does f prime of x switch sign at x equals 1 and x equals 2? And what does it mean when f prime of x switches sign? That means the derivative goes from positive to negative or negative to positive. And what does that mean when the derivative switches sign? It means the slope switches sign. And so the slope goes from increasing to decreasing or decreasing to increasing. Right? So now just look at the graph here and see what's going on with the slopes. From negative 2 to 1, the slope is positive because it's going up. From 1 to 2, the slope is negative because it's going down. And then from 2 to 4, it's still negative, it's still going down. So we see that from negative 2 to 1 and from 1 to 2, there was a switch in the slope. So that means this is a point where the first derivative of f switched signs, and therefore the second derivative of g switched signs, and therefore that this is a inflection point on the graph of g. But when we look at x equals 2, we see that it goes from negative to negative, so it didn't switch sign, and therefore that this is not an inflection point on g. Let me just write this out. So at x equals 1, f prime of x switches sign. Specifically, it switched from positive to negative. Therefore, it's an inflection point. Move that over. Therefore, it's an inflection point. But if we're looking at g of x, if we're looking at x equals 2, f prime of x does not switch sign. Therefore, it's not an inflection point on the graph of g. All of these are on g of x. And then looking at the original question, oops, I did not mean to do that, my bad. Okay, so the question is, how many of these values are x coordinates of points of inflection? Well, we said that x equals 1, that's good. X equals 2 is no bueno. So the final answer is just x equals 1 is the inflection point. And if we want to justify our answer, we'd say that f prime of x is only f prime of x switches sign at x equals 1, but f prime of x does not switch sign at x equals 2. So therefore x equals 1 is the only inflection point on the graph of g. Okay, and looking at points, we'd get 1 point for correctly saying that x equals 1 is a possible inflection point, or is an inflection point, because f prime of x switches sign. We'd get another point for saying that x equals 2 does not work, because f prime of x does not switch signs. And we get a third point for an explanation that x equals 1 is the only inflection point. So like as a coordinate, it would be 1, comma, g of 1. This is the only inflection point on the graph of g, because it's the only point where, again, f prime of x switches sign. Okay, so that was question 5. Now let's look at question number 6, the last one. Okay, question number 6. And before we get started, yes, this is definitely a challenging problem for sure. Like, there's just so much going on here. There's a tangent line to some curve here. There's this variable w. There's this variable k. And then, we have all this. And there's this triangle PQR. That comes into play at some point. Like, There's just so much stuff going on. But let's try to really understand what's going on by like reading, taking the time to read the problem and not rush to looking at part A already. So we have a figure above, line L is tangent to the graph of y equals 1 over x squared. So we have this curve here, and then this is the tangent line at point P. And the coordinates of point P are w comma 1 over w squared. I think that's worth labeling. W comma 1 over w squared, where w is greater than 0. And then point Q, which is like on the same, which is like, vertical to P, that has coordinates w comma 0. Let's label that as well. And then line L, which is this tangent line, it crosses the x-axis at the point R, and R has coordinates k comma 0. So find the value of k when w equals 3. So when w is 3, so this is 3 comma 1 over 3 squared, and this is 3 comma 0, what is this value of k? And since k is very closely associated with line L, a good strategy might be finding the equation of line L, right? So to find the equation of line L, first we're probably going to find the slope of line L. So a good starting step would be the slope of the line L. And since L is the tangent line to this graph at W, we'll take the derivative of x to the negative 2, which is y, which comes out to be negative 2 over x cubed. So we can take the slope, and it's at point W, right? And since in this question W is 3, we're going to take the derivative like we did and evaluate this at x equals 3. So negative 2 over, instead of x, we're going to put 3 cubed, which comes out to be negative 2 over 27. So this is the slope of line L, because that's the slope of the tangent line at point x equals 3. So now, what else can we do? Well, we have this point here. We have w comma 0, and we have this point here, w comma 1 over w squared, right? So since w is 3, this point P is 3 comma 1 over 9. We have point 3 comma 1 over 9. And then that point, 3 comma 1 over 9, that's on line L. So we have the slope of line L here. We have one of the points on line L, and I think we can use that to find k. Alright, so we want to find k, and so therefore we also know that point k comma 0 is on the line as well. So we have 3 comma 1 over 9, and we have k comma 0. These are both points on line L. We have the slope of line L, so we can use our equation to find the slope the old school way, not using derivatives, using algebra, and we can use these 2 points and our slope to find k. So remember the formula y2 minus y1 over x2 minus x1 to find the slope. Well, we have our our 2 coordinates, we have our slope. So we'll say if this is this is point 2, this is point 1, this is going to be 0 minus 1 over 9 over k minus 3 being equal to the slope, which is negative 2 over 27. We'll bring the k over 3 to this side, and we'll bring the negative 2 over 27 to this side. So we'll get k minus 3 is negative 1 over 9 times 27 over 2, negative 27 over 2. The negatives cancel. This goes away. This comes to 3. So k minus 3 equals 3 halves. K is equal to 3 plus 3 halves, or 9 halves. Okay, and that was part A. And in terms of points, you'd get 1 point for taking the derivative and putting in x equals 3, and you get another point for properly solving the value of k. Okay, now let's look at part B. So for all w greater than 0, find k in terms of w. So what that means is that instead of having a w equals 3, like a specific value, we're just going to have a general equation in terms of w. Okay, so we're going to do the same steps. We're going to take the derivative of our function, but instead of doing it at x equals 3, we're going to do it at x equals w. That's going to be negative 2 over w cubed. And then instead of having 3 comma 1 over 9, we're going to have w comma 1 over w squared, and we'll still have this point k comma 0. Alright, these are the 2 points, P and R, that are on line L. So we have the slope, we have the 2 points. Putting that together, we have 0 minus 1 over w squared over k minus w equals negative 2 over w cubed. And then bringing the w cubed over to this side and bringing the k minus w over to that side gives negative 1 over w cubed, or w squared, sorry. 1 over w squared times w cubed is equal to negative 2 times k minus w. And then this is going to become negative w is equal to negative 2k plus 2w. We distributed the negative 2 over, and then we can bring this w over to this side, and we'll get negative 3w is equal to negative 2k. And then dividing both sides by negative 2 gives us k is equal to 3 over 2w. So that's our equation for k in terms of any w value. And for points, we'd get 1 point for setting up this slope form, and we'd get another point for the right answer. Okay, now part C, pretty easy stuff. Suppose that w is increasing at a constant rate of 7 units per second when w equals 5. What is the rate of change of k with respect to time? So we're going to have to use what we got in part B, which is k is equal to 3 over 2w. And then since we want to find how these two change as time changes, we're going to take their derivatives with respect to time. So we'll take this whole equation and differentiate it with respect to time. That's going to give us dk dt is equal to 3 over 2 dw dt. And then suppose that w is increasing at a constant rate of 7 units per second. So dw dt is 7. Equal to 3 over 2 times 7, which is 21 over 2. And that's what they wanted, right? When w equals 5, what is the rate of change of k with respect to time? Well, when dw dt is 7, like they said, this is dk dt, the rate of change of the variable k with respect to time. That was just a little quick 1-point question, right? And then now let's look at the final part, part D, which is quite challenging in my opinion. Okay, so looking at part D now. Suppose that w is increasing at the constant rate of 7 units per second when w equals 5. What is the rate of change of the area PQR with respect to time? Determine whether the area is increasing or decreasing at this instant. Okay, so first, let us look at this triangle in a bit more detail, right? Let's draw a bigger picture of this PQR. And let's label the points. So at P, the coordinates were w 1 over w squared. At Q, the coordinates were w 0, and then at R, the coordinates were k comma 0, right? And then they're asking us about the area, so it's probably going to be wise to find an equation for the area. The formula for the area is 1/2 base height. So let's find an equation, or find an expression for the base and for the height. So since this point here is k and this point here is w, this distance here is going to be k minus w. It's like the distance in between those two values. And then the height, we're going from y equals 0 to y equals 1 over w squared. So this height is 1 over w squared. Okay? So now that we have the base and the height, we can rewrite the area formula as 1/2 times k minus w times 1 over w squared. And then another thing we can do is that we want to figure out what's going on when w is 5, right? So we don't really know what k is at that moment. So we should probably find a way to replace k with w. And how do we do that? Well, remember in part B, we said that k is equal to 3 over 2w. Well, that means I can take my k and replace the k with 3 over 2w minus w times 1 over w squared. And just a bit of algebra, this becomes 1/2 w, this becomes 1/4 w. So this is going to be w over 4. And then multiplying this by 1 over w squared, I keep doing that, gets us 1 over 4w. And basically what we said is that the area is equal to 1 over 4w. And then remember, I want to take the derivative of this with respect to time, because we want to find how much the area is changing with respect to time at a certain point, right? So if I take the derivative of this, I'll get dA dt is equal to the derivative of 1 over 4w, right? And let's do the 1 over 4w part in a separate section. So I can pull out the 1/4. I'll get ddt 1 over w, or w to the negative 1. And if I do this, I'm going to get negative 1 over 4w squared. And then because of the chain rule, I'll get dw dt, if you want to think about it by implicit differentiation. Right? So I have this being equal to this, so I'm going to substitute that in. I'll get dA dt is negative 1 over 4w squared times dw dt, and we'll just plug in these values. So we want to figure out what's going on when w is increasing at the constant rate of 7 units per second. So dw dt is 7, and then w equals 5, right? So we'll just plug in w equals 5, and dw dt is 7 to get us negative 1 over 4 times 25, because that's 5 squared, times dw dt times 7. And this comes out to be negative 1 over 100 times 7 is negative 7 over 100. That's the area. And then they also wanted to know, is the area increasing or decreasing at this instant? Well, since the derivative of area with respect to time is negative, that means at this point, area is decreasing as time increases. So since dA dt at w equals 5 is less than 0, the area is decreasing. You'd want to write that out. Okay, and in terms of points, we'd have 1 point for this part here, where you're finding the area in terms of k's and w's and all that. You get another point for this derivative part down here. You get another point for correctly substituting in the values for w and dw dt. And then you get a 4th point for correctly stating that the area is decreasing because dA dt at w equals 5 is less than 0. Okay, so that was the culmination of the 1999 AB Calculus exam. I hope you found this video helpful, and I will see you next time. Goodbye.